All right, in this video, we are going to talk about the binomial distribution. So, the binomial distribution is a probability distribution for the number of successes in a sequence of Bernoulli trials. Okay, so you have some Bernoulli trials, and you say like you have 10 trials, right? That you run through, and so when you run those 10 trials, you're going to get some number of successes, and the this distribution, the binomial distribution, right? It gives the probability that you would have some number of successes in there. So if you had 10 trials, right, you could have 0 successes, 1 success, right, 2 successes, all the way out to 10 successes, right? And so, and then you would have the probability for each of those, right, listed out. Okay? So that's what the binomial distribution is. And let's see, we're going to cut past this one. Here's an example of what a probability distribution might look like for the number of successes. Here we would have 3 trials, right? Or whatever the experiment is. Actually, I guess I can. This is the pinworm. I'm not going to work this problem here in this video, but this is the pinworm experiment that we've already identified, right, as Bernoulli trials, right? So we have pinworm infestation, which is commonly found in children, can be treated with the drug parental pamoate. According to the Merck manual, the treatment is effective in 90% of the cases. Suppose that the 3 children with pinworm infestation are given parental pamoate. So in the previous video, right, we talked about that success was that a child is cured, right? And so we're treating 3 children with this medicine, and then those are your 3 trials. And the thing that we're interested in is how many successes did we have? How many of the children were cured? Okay? And so the possible values that you might have is none of the children are cured, right? Or one of the children is cured, or 2 of the children are cured, right? Or all 3 are cured. Okay? So those are the possibilities that you might have of the 3 trials for the number of successes. Okay? And then over here you would have the probability of the successes. Okay? So these numbers came from applying the rules of probability that we talked about in the in chapter 4 to the situation of this this experiment. Okay, so I haven't given you the details on that, but in this video I'm not going to focus on those details, but rather how to come up with these probabilities using the following binomial probability formula. Okay, so if we have a binomial random variable, right? It's let X denote the total number of successes in n Bernoulli trials, with the probability of success being P. Then the probability distribution is given by this formula right here. So the formula looks kind of bad at first, but it really is not too bad to deal with, especially if you're using Desmos, right? It's pretty straightforward, and I'll show you how to use this thing. So this gives the probabilities that I showed you in that probability distribution before. So if you have a random variable like this that represents the number of successes in n Bernoulli trials, that is a binomial random variable. It's a discrete random variable. And the binomial random variable is said to have the binomial distribution with parameters n and p. So n is the number of trials, right? And p is the probability of a success in that trial. Okay? So let's go back and take a look at, I think here is that probability distribution that I showed you for the experiment with treating the 3 kids for pinworm infestation. So here I am just using this formula, and let me take a screenshot of that, and then we can look at it on the next slide as well. Okay, so here's an example. So this is for the pinworm infestation experiment that we had. We had 3 kids, right? We treated them with some medicine, and we were looking for how many children were cured. Okay, and so the number of trials would be 3, right? And then x would be the number of successes. So that would be 0 in this particular example here, right? And so the probability, what we would do is put the n in here, right, for 3 in for n, and then 0 in for x into this. And then for the probability p, we would put 0.9. All right, and then 1 minus p, it would be 0.1. And then n minus x, that would be the number of trials, right, minus the number of successes. So in this case, that would be 3 minus 0, right? So again, it looks kind of hard to do this, but if you evaluate this on Desmos, right, if I had Desmos popped up, it should be somewhere. So that would be NCR. Remember, that does the binomial coefficient. Top number is 3, the bottom number is 0. And then it would be P, which is our probability of success, 0.9. Right? And then to the number of successes, right? The number of successes goes in the top. And then it's 1 minus 0.9. 1 minus the probability of success, or that's actually the probability of failure. And then the exponent is 3 minus 0. Okay, and you can see we get that value .1 or 0.001. Okay. All right, and so now if I want to calculate the probability of 1 success, right, I would do NCR 3, 1, 0.9 to the 1, right, because for 1 success, X is the number of successes in our formula, and then 1 minus 0.9, the probability of success, to the, and then it would be 3 minus 1, right? The number of trials minus the number of success. You can see I get this value right here, 0.027, okay? And same thing on the other one. Do one more, right? This one here, do NCR 3, 2, and 0.9. In this case, we have 2 successes, right? International keyboards. My keyboard's acting kind of weird. Okay, and 1 minus 0.9, and 3 minus 2. And you can see I get this value right here. All right, so that formula gives us, this formula here, right, gives us the probability that a binomial random variable equals some number of successes over here. Okay, so that's how you would calculate that out with this formula. All right, so here is the procedure for finding a binomial probability formula. You have to make sure these assumptions are satisfied, that you have n trials that are to be performed, so, and that would be your number n in the formula. Then each trial, right, has to have exactly 2 outcomes, success or failure, right, and that's it. The trials are independent, meaning that what happened on one trial does not affect in any way, right, what happens on the any other future trial. Okay. And then the probability of success has to remain constant from trial to trial. It doesn't change, right? The probability of success doesn't go up or down, all right? So those are the assumptions that you have to have. So step number one, right, is in calculating these probabilities is to identify a success, all right? So you have to figure out what's the success, and then two, what is the probability of success? So that they're going to give you some probability in these problems that we're going to work, and so the main thing to do is that kind of, to me, I would go with the probability that they give you as being the probability of success, and identify that whatever they're talking about that in relation to that probability as a success. All right, next up is determine the number of trials. That would be n, right? And so n and p would go in these places in the formula, and then to calculate the probability, right, what you would do is plug in the value for x that you need. Okay. All right. So I think we are ready to start working these problems. All right. So the first problem is 5.78. In that it says the probability is 0.314 that the gestation period of a woman will exceed 9 months. In 6 human births, what is the probability that the number in which the gestation period exceeds 9 months is A, exactly 3, B, exactly 5, C, at least 5, right? D, between 3 and 5 inclusive. All right. So the thing that we want to do is go back through, right, these steps, right, and figure out what is the success, all right, and what's the probability of success. That's going to be the first thing, right? So it says the probability is 0.314. So they're giving you a probability. So in this problem, that is probably the probability of success, all right? It says that the gestation period of a woman will exceed 9 months, all right? So in this, that's defined as a success, okay? So now you might be thinking, well, how is that a success, right? Again, don't try to, you can't associate, the normally positive connotation that you have with the word success with this. Just kind of go with it, because otherwise you're going to have more work to do, okay, in this problem. So a success in this case is that the gestation period exceeds 9 months. So the pregnancy lasts longer than 9 months. All right, and so if that's the case, right, if the success is that the gestation period exceeds exactly 9 months, right, then what we need to, then the probability of success P, right, is going to be 0.314, okay? So we've done that. Next up, right, we need to figure out our number of trials, right, step 3 here. And in the problem, it says that in 6 human births. So they went and looked at the gestation period for 6 human births, right? And so the number of trials is 6. So here we would say n equals 6, okay? Okay, so now what they want to know is they want us to calculate some probabilities associated with that. So we know, right, what our formula is going to be. Our formula, right, is going to be given by this formula, right? The probability that capital X equals X equals n choose X times p to the x times 1 minus p to the n minus x for x equals 0, 1, 2, all the way out to n trials. Okay. All right, and we know what these values are for n and p, so we can fill this in, right? So this formula would be n, we know, is 6, right? So this would be 6, choose x. And then the probability of success is 0.314 to the x. And then 1 minus p would be 1 minus 0.314. And then n minus x would be 6 minus x. Okay? And this formula would be valid for x's in the range from 0, 1, 2, all the way out to 6. Okay? All right, so that's our formula. I'm going to go ahead and put that in Desmos so we can start calculating that out. And so let me show you the best way to put that in Desmos. Now the best way to do that is just put it as p of x and then equals, and then NCR 6x. So you can see I'm leaving the x in there, right? 0.314 to the x, and then 1 minus 0.314 to the, and then in parentheses 6 minus x. Okay, so that's what the formula is going to look like in Desmos. You'll get some kind of crazy graph, right, that looks like this, but you don't have to worry about it. You can just turn it off. All right, so there's our formula. All right, so going back to the problem, right, in part A, they want us to calculate what's the probability that x equals 3, right? I think that's it. Let's just double check. Yeah, part A, what is the probability that the number of successes is exactly 3? All right, so if you have it punched in this way, then all you have to do to plug in the 3 is just put p of 3 there, and it will plug that in for you. And you can just read off the value there. So if we're rounding to, say, like 3 decimal places, that's going to be 0.200, right? Because we would round this up to a 0, and that's going to cause all of these things to be rounded up. So that's what we get for part A. All right. All right. In part B, they want to know exactly 5, right? So what's the probability that the random variable is exactly 5? So again, on that one, all you would have to do is plug in the 5. If you have it set up the way I do, right, you can just type p of 5 and it will plug it in for you. And then you can just read off the answer here. So we can see that we get 0.013. Okay. Then next one, that's part B. Next one would be the probability that C is at least 5. Okay. So at least 5. So at least 5 would mean greater than or equal to 5, right? Like this, all right? And so if the number of successes in the 6 trials was greater than or equal to 5, that means that the probability that x is greater than or equal to 5 is the same as the probability that x equals 5 or x equals 6, right? Like so. Okay? And then what you would do is we have to calculate the probability of the OR of 2 events, right? That is going to be using one of the addition rules, either the general addition rule or the special addition rule, right? And to figure out which one, right, we have to ask ourselves, are these two events, right, on either side of the or, are they mutually exclusive? In other words, is it possible that I do this experiment? I go to 6 births, right, and I observe how many of the women have gestation periods exceeding 9 months. And I get exactly 5 that are longer than 9 months. And also at the very same time, 6 that are longer, right, than 9 months. Well, no, that can't happen, right? Because it's 5 or 6. It can't be both. So these two events are mutually exclusive. So that means I can use the special multiplication or addition rule that says all I've got to do is add these two events together, all right? Like so. All right, we already found that the probability of x equals 5, we already know that. That's 0.013. And the probability that x equals 6, I can find that. Again, if you have it punched in like I do, it's just easy to find that. And I get here, p of 6 is this very, very small number, right? So 0.001 to 3 decimal places, 0.001. Okay, so that comes out to be 0.014, like that. All right, part D, it says, what's the probability that it's between 3 and 5 inclusive? All right, so between 3 and 5 inclusive would be written like this. What's the probability that x is between 3 and 5? Inclusive means that you should include the 3 and the 5 together, okay? So, again, you would do this exactly the same way as here, right? That's going to be the probability that x is equal to 3, or x is equal to 4, or x is equal to 5, right? And I have the or of a bunch of events, so I'm going to have to use one of the addition rules. Should I use the special or the general? Well, I have to ask myself, are these mutually exclusive? Can I have 3 successes and at the same time have 4 successes, or at the same time have 5? No, I cannot, right? So these are mutually exclusive, so I can use the special addition rule, and the special addition rule says just add up the individual probabilities. So if I add up probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5, right, I get that. And then 3 we've already done, right? We get 0.200. For 4, I don't think, do we do that one yet? No, we did not. So we'll have to do that one. And then 5 we've already done. 5 is 0.013 to 3 decimal places. So if we want 4, let's go ahead and do that and plug that into our formula. So to 3 decimal places we get 0.069. All right, and then we can add those up. Let's go ahead and do that. So we get 0.200 plus 0.069 plus 0.013, I believe it is. So we get 0.282 on that probability. All right. If you might be thinking that could I just punch it in like this, and you absolutely can. That would be probability of 3 plus probability of 4 plus the probability of 5. So you can save yourself a little time by doing that as well. You can see that here, though, because we rounded it off in these intermediate steps, we got a slightly higher value than we did here. If we rounded to 3 decimal places, that would be 2.281 here on this one. So this one is actually more exact doing it this way. Here I'm off by a little bit. on that probability because I rounded in these intermediate stages and did my calculations. Okay. All right. So that is our first example, and what I will do is to split these rest of these things in a separate video.